Let's talk about integration by parts. Now, integration by parts is essentially product rule, but for integration instead of differentiation. Here's your formula. It states that the integral of u times v, where u and v are both functions, is equal to u times the integral of v minus the integral of u prime times the integral of v. This formula can easily be proven by differentiation and by using product rule. So if we take the derivative of this, the integral goes away and it becomes uv is equal to, for this we have to use product rule, and this becomes u prime integral v minus plus uv, and this becomes minus u prime integral v because the integral goes away when we differentiate. So these two terms cancel out and we're left with uv is equal to uv. Therefore, this is our formula for integration by parts. Let's start with the simple one. This is the integral of 2x times e to the x with respect to x. There's one thing to notice. When we look at our integration by parts formula, which I'm going to write really quickly here, there's one function, u, that stays the same here and that we differentiate here. And there's another function, v, that we integrate both times it's used in the formula. So it's important to choose our u and v wisely. One of them we're going to differentiate and the other we're going to integrate. So here I'm going to select this as u, because if I were to take the derivative of the function 2x, it simply equals 2. And that makes integrating our functions much easier because this u prime simply becomes a 2. Therefore, I'm going to make this u integral v, so 2x, integral of e to the x with respect to x, minus the integral of u prime, which is now just 2, times the integral of v, which is e to the x dx still. Now, the thing with e to the x dx is that the integral of this is simply itself, so this becomes 2x e to the x minus the integral of 2 e to the x dx. Now, the integral of this is simply itself once again, so I'm going to finally rewrite this as 2x e to the x minus 2e to the x plus c, and this is our final integral. Let's look at another slightly different example. This is the integral of ln x with respect to x. Now, there's no elementary antiderivative for ln x, and initially this might not even look like a product, so it might be strange why we're actually using integration by parts. However, I'm going to rewrite this as 1 times ln x dx. When we take the integral of this, it becomes apparent how we can use integration by parts, and here's the important part. In our formula, we never have to directly integrate whatever we decide to be u. Since we don't know the integral of ln x, I'm going to set this as u and this as v, because we know how to integrate 1. So therefore, this becomes u times integral of v, which is ln x times x, because the integral of 1 is x, minus the integral of u prime, which is 1 over x, integral v, which is x once again. Now, these x's cancel out, so all we're left with is ln x times x minus, this becomes the integral of 1, which is simply x. So the integral of ln x is x ln x minus x plus c. Let's look at one more problem. This is x cubed e to the x with respect to x. Now, we could do this with the same strategy that we used earlier. So we could differentiate this one constantly and integrate this one constantly. But if you'll notice, when we differentiate x cubed, the x doesn't go away like it did with 2x. It simply becomes a 3x squared. If we want to take the integral of 3x squared e to the x, we're going to have to use integration by parts again. And so for this integral, we have to use multiple applications of integration by parts. But there's actually a shortcut. Let's write out our formula one more time. Let's imagine that our integral of u prime integral v had to be integrated using integration by parts again, and we kept the same u and the same v. Well, this is then going to become u prime double integral of v minus integral of u double prime double integral of v. And you can see a pattern here. If we were to do that again for this function, we would get the same thing, but instead of double integrals and double prime, we would get triple integrals and triple prime. So again, there's clearly a pattern. One function we will continue to differentiate over and over again, and the other we will continue to integrate over and over again. So first, let's choose our u and choose our v. Since we're differentiating u, I want to differentiate this function over and over again, because by the third derivative, this function will be a constant, and any more than that, it'll be 0, and that will greatly simplify my expression. This is the function I want to integrate, because e to the x has the special property of simply not changing whenever I integrate it. So therefore, this will be my u, and this will be my v. And now, we're going to use the tabular method, also known as the di method. So firstly, let's set up our table. Because it's called the di method, I'm going to write d and I, and these will be the two columns of our table. Now d is whatever we're differentiating, so that's going to be our u, which is x cubed. I'm going to write x cubed here, and therefore I has to be e to the x. All we're going to do as we go down this d column is simply differentiate. So x cubed is going to become 3x squared, which is going to become 6x, which will become 6, which will become 0. Now e to the x stays the same, so for every integral of e to the x, it's simply e to the x with no change. Now let's look at all of our collected terms from this formula over here. So what we actually have firstly is u times the integral of v minus u prime times the double integral of v, and if we keep on going, it'll be u double prime times the triple integral of v. So what we're doing here is we're going to take u times the integral of v, and then we're going to take u prime times the double integral of v, and so on and so forth, u double prime times the triple integral of v, and we're simply going to multiply them together. However, there is a minus in the integration by parts formula, and so if we keep applying this, this is all actually going to be nested under a minus sign, and so our signs are going to keep alternating. That's why we also have pluses and minuses alternating in these columns. Finally, all we have to do is combine all of this information and multiply everything together. So our first term is going to be positive x cubed times e to the x. So I'm going to write x cubed e to the x. Our second term is going to be minus 3x squared e to the x. So minus 3x squared e to the x, then plus 6x e to the x. So plus 6x e to the x, and finally minus 6 e to the x. Now we have to add our c, and this becomes our final integral using the DI method, which is essentially the shortcut to using integration by parts multiple times. Here's a unique problem. We have e to the 2x times cosine of x over 4 with respect to x. Now, we can't use the earlier method, because the only reason the earlier method worked was because one of the derivatives, after we would take the derivative over and over again, would reduce to 0. So eventually we'd get something multiplied by 0 and our terms would end. However, e to the x, when we integrate or differentiate it, will simply remain itself, albeit with a few coefficients, and cosine will simply cycle through cosine, sine, and negative sine and cosine over and over again. Once again, maybe with different coefficients. So sometimes the terms don't always reduce, no matter how we choose our u and v. For this, we have to make the integral reappear, and here's what that means. First, let's draw out our DI table and take our terms. So here, because we're cycling, it's not necessarily super important what we use as u and what we use as v, so I'm going to say this is going to be cosine x over 4, and this is going to be e to the 2x. So first, let's differentiate. This becomes negative sine x over 4, and because of chain rule, it'll be divided by 4. We differentiate once again, we get negative cos x over 4 divided by 16, then sine x over 4 divided by 16 times 4 is 64, and so on and so forth. This e to the 2x becomes e to the 2x over 2, e to the 2x over 4, e to the 2x over 8. Now, this isn't immediately obvious, but first let's think about what we're actually doing with the DI method. So, when we go through our normal processes of using this method, such as taking the plus, minus, taking these all multiplied, and these all multiplied, what we're actually doing is finding the integral of this product. So therefore, if we were to start, say, here, and we were to take this multiplied, we would be finding the integral of this product. And what this means is that by the time we get to this third row over here, anything beyond that will actually be the integral of negative cos x over 4 over 16 times e to the 2x over 4. So really quickly, let's write all of these products together until we get to this integral and see what we have. So firstly, we're going to have positive cosine x over 4 times e to the 2x divided by 2. Then we're going to have this negative and negative cancel each other out, so we're going to have plus sine x over 4 divided by 4 times itself, so 16, and then e to the 2x. Now, I'm not going to take this product with this immediately, because I'm going to rewrite it, so minus the integral of cos x over 4 over 16 times 4 e to the 2x. And now, I can remove this 16 times 4 in the denominator, and what I'll have here remaining is actually this exact integral. So let's rewrite our expression and make it stand out even more. Now, I'm going to set this entire integral that we're solving for equal to I, and I'm going to say I is equal to cosine x over 4 e to the 2x over 2 plus sine x over 4 e to the 2x over 16 minus, I'm going to take the 64 outside, so minus what we're left with is actually I divided by 64. And now all we have to do is solve for I. All we have to do is move I to the other side, and we're left with 65I over 64 is equal to this whole expression. So what I'm going to do is I'm going to multiply this by 64 over 65, and what we're going to get is 64 cos x over 4 e to the 2x over 265 plus 64 sine x over 4 e to the 2x over 1665. And now this is going to simplify to a 32, this is going to cancel, this is going to simplify to a 4, this is going to cancel. So now let's write our final answer. So we're going to say I, which is once again the integral of e to the 2x cosine x over 4 with respect to x, is equal to 32 cosine x over 4 e to the 2x over 65 plus 4 sine x over 4 e to the 2x over 65 plus c, because it's an indefinite integral. And this is our final answer. Remember, what we did was first we used the DI method until we made the original integral. I'm going to say this is u, this is v. We kept cycling through it until we got u and v again. And then, once we had the original integral, we moved it to the other side. So we get I is equal to some math, maybe minus 4i. And then all we have to do is solve for our new integral, and this is what we get. Let's look at a different kind of integral, e to the square root of x. Now, we don't immediately have anything that we can multiply, so we could use integration by parts with 1, but if we were to take the derivative of this, it'd be e to the root x over 2 root x, and that simply becomes more messy. So what we're going to do is a u substitution that looks a little different. Now, once again, most u substitutions are used to simplify the expression to reduce the number of terms, but we're going to introduce a term by saying here a function of u is actually equal to x instead of the other way around. This means that du squared over du is equal to d over du of x. Therefore, 2u is equal to dx over du, and we can say that du times 2u is equal to dx. Now, when we have a 1 dx, we now have 2u du, and because u squared is equal to x, this becomes e to the u. So let's rewrite our integral as the integral of e to the u 2u du, and now let's use our integration by parts. So this one doesn't actually need tabular method, this simply is u, and this is v. So we start with u, the integral of v is integral of e to the u, which is simply e to the u, minus the integral of u prime, which is 2 integral of v e to the u. So this becomes 2u e to the u minus 2e to the u plus c. Once again, we're not done, we still have to put things in terms of x, but we simply say u is equal to square root of x, and therefore this becomes 2 root x e to the square root x minus 2e to the square root of x plus c. And this is our final answer.